So let's take a look at strategy for integration. Now in this video we'll just be trying to come up with many different strategies to try to evaluate various integrals. So for number one we have the integral of sine of x plus secant x all over tangent x dx. And so whenever you have a fraction, it's always a good idea to see if you can break it up. Now since there is a plus sign here, I can break up the fraction into two separate fractions and say sine of x over tangent x and then plus secant x over tangent x. Now sine of x over tangent x, I can rewrite tangent x. I can rewrite it as sine of x over cosine x. So then when I multiply by the reciprocal, cosine x over sine of x, realize the signs will cancel and we're left with just cosine x. And now for secant x over tangent x, once again I can rewrite it as secant x over sine x over cosine x. So then I can go ahead and multiply by the reciprocal, and I'll rewrite secant as 1 over cosine, since cosine is the reciprocal of secant. So we have 1 over cosine times the reciprocal of sine over cosine, which is going to be cosine x over sine x. Realize the cosine x's do cancel, and so we're left with 1 over sine x, which is cosecant of x. So I can go ahead and say that sine x plus secant x over tangent x can be rewritten as cosine x plus cosecant of x. So now I can go ahead and rewrite it as the integral of cosine x plus cosecant x dx. So the integral of cosine x is obviously just sine x. And then for the integral of cosecant x, once again, this is probably a good integral to have memorized. It's just going to be negative natural log absolute value of cosecant x plus cotangent x. And then since this is an indefinite integral, we need the plus c at the end. So that's the final answer. So now for number two, we have the integral from -1 to 1 of e to the arctangent of y over 1 plus y squared dy. Whenever you have a problem like this, you try to look for some kind of obvious substitution first. So I'm looking at arctangent of y, and we know that the derivative of arctangent or inverse tangent of y, if I go ahead and rewrite y, is going to be 1 over 1 plus y squared. Well, if I go ahead and use u substitution, I'll be able to cancel out that 1 plus y squared in the denominator. So let's go ahead and use u substitution. If u equals, I'm going to set u to be arctangent of y or inverse tangent of y. So then du, or the derivative of inverse tangent of y, is 1 over 1 plus y squared dy. Then if I isolate dy, dy is going to be equal to, well, we're going to divide by the, or multiply by the reciprocal when we divide. So we have 1 plus y squared times du. So when I substitute everything back into the integral, we have the integral from -1 to 1 of e to the u, because I made u equal to arctangent of y, over 1 plus y squared times dy, and dy once again is equal to 1 plus y squared times du. Realize those will cancel, and so we're left with the integral from -1 to 1 of e to the u du. And the integral of e to the u is just e to the u. So we have, and I'm going to replace the u, once again u is equal to arctangent of y. So we have e to the inverse tangent of y. Now we can go ahead and evaluate from the y bounds of -1 to 1. So when I plug in 1 for y, we'll get e to the inverse tangent of 1 minus e to the, when I plug in -1, e to the inverse tangent of -1. Now in order to evaluate this, let's go ahead and draw the graph of arctangent of x. Now it looks something like this, and it has two asymptotes. The horizontal asymptote on the top is going to be at y equals pi over 2, and the bottom horizontal asymptote is going to be at y equals negative pi over 2. So we can say that arctangent, or the function for arctangent, ranges from negative pi over 2 to pi over 2. So now for inverse tangent of 1, another way to think about this is, what do we take the tangent of to get 1? And the value once again has to be in between negative pi over 2 and pi over 2. Well, that's going to be positive pi over 4. So e to the positive pi over 4 minus, now for inverse tangent of -1, what do we take the tangent of to get -1? And that value has to be between negative pi over 2 and positive pi over 2. Well, that's going to be 7 pi over 4, because inverse or tangent of 7 pi over 4 gives us the value of -1. And 7 pi over 4 is between negative pi over 2 and positive pi over 2. And so that will be the final answer. Now another way to think about this is by also using the unit circle. So if we go ahead and draw out the unit circle, our range of arctangent values must be between negative pi over 2, which is going to be negative 90 degrees, and positive pi over 2, positive 90 degrees. So we're basically looking for this region here. Obviously pi over 4 is 45 degrees. That's pi over 4, and 7 pi over 4 is negative 45 degrees. So both of those fall in the range between negative pi over 2 and pi over 2. So now for number 3, we have the integral of x minus 1 over x squared minus 4x minus 5 dx. So realize this fraction is bottom heavy, and I can go ahead and break up the denominator into linear factors. So I go ahead and just rewrite the fraction x minus 1 and then break up the denominator. X squared minus 4x minus 5 can be broken up into x plus 1 and x minus 5. Because we do have two distinct linear factors in the denominator, we can go ahead and use partial fraction decomposition. So we have x minus 1 over, I'm just going to go ahead and rewrite the fraction. And so that's going to equal a over one of the factors, x plus 1, and plus b over the other factor, x minus 5. Once again, I'm going to have to multiply both sides by x plus 1 times x minus 5. So when I do that, that will cancel. We have x minus 1 on the left side of the equation. I can go ahead and cross multiply. So then we have a times x minus 5 plus b times x plus 1 on the right side of the equation. Once again, I need to plug in different values for x so I can cancel out one term and evaluate the other one. So let's go ahead and first start by plugging in 5 for x. So when I do that, the a term will cancel. So we're going to get 5 minus 1, which is 4, equals, the a term obviously will cancel, and then we get 5 plus 1, which is 6, so then 4 equals 6 times b. So then if we isolate b, b is going to equal 4 over 6 over 2/3. Now same thing we're going to do for a here. Let's plug in negative 1 for x, because negative 1 plus 1 is 0, that will cancel out the b term. So we have negative 1 minus 1, that's going to be negative 2, equals negative 1 minus 5 is negative 6, so negative 2 equals negative 6 times a. Then isolating a, we get a equals negative 2 over negative 6. Negatives will cancel and we'll get 1/3. So going back to our decomposed model here, we can plug in our terms. So a is obviously 1/3, so we have 1/3 over x plus 1, plus b is going to be 2/3, so 2/3 over x minus 5. So now we can go ahead and integrate that with respect to x. Now the integral of 1/3 over x plus 1 is going to be 1/3 times the natural log of the absolute value of x plus 1, and then plus the integral of 2/3 over x minus 5, which is going to be positive 2/3 natural log absolute value of x minus 5. And then this is an indefinite integral, so we need to add the plus c at the end. And that's the final answer. So now for number 4, we have the integral of x times sine squared x dx. Now we do have two functions being multiplied to each other, x and sine squared x. So it could be reasonable to use integration by parts, but if you go ahead and pick u as x and dv as sine squared, obviously you can easily derive x, but it's difficult to integrate the dv, which is sine squared of x. So what I'm going to do first here is to actually rewrite sine squared using the half angle formula. So I can rewrite it as x times, well, sine squared of x using the half angle formula is going to be 1 minus cosine of 2x over 2. So if I go ahead and distribute the x, we get x minus x times cosine 2x over 2. And now I can go ahead and put that underneath the integral and integrate with respect to x. Now 1/2 is a constant, so I can take that outside the integral. We have 1/2 times the integral of x minus x times cosine 2x dx. Now the integral of x is obviously just going to be x squared over 2. 1/2 is a constant, so 1/2 times x squared over 2. And then minus, now we have the integral of x times cosine of 2x. So if I go ahead and rewrite that separately, integral of x cosine of 2x dx. Since we do have two functions being multiplied by each other, it's a good idea to use integration by parts, specifically the tabular method. So once again, for the tabular method, I'm going to make 3 columns here, the u column, the dv column, and the plus minus column. So now for the u, I'm going to pick the u to be x, and I'm going to pick dv to be cosine of 2x. So I'll put u as x, dv as cosine 2x dx, and obviously the first row is going to be positive. Now we can just use the first scenario of the tabular method where we derive the u column until we get to 0. So derivative of x is 1, derivative of 1 is 0. The integral of cosine 2x is going to be 1/2 sine of 2x, and the integral of 1/2 sine of 2x is negative 1 over 4 cosine of 2x. We can alternate between plus and minus. And so now I'm going to go ahead and circle around these terms until I hit the bottom row, and then I can go ahead and evaluate. So we're going to multiply x and 1/2 sine of 2x, so we get 1/2 x times sine of 2x. we do have a minus here, so minus, we have 1 times negative 1/4 cosine 2x, so minus a negative 1/4 cosine of 2x, and then we have plus the integral of the last row. And the integral of 0 times just negative 1/4 cosine 2x, that's the integral of 0, which is obviously still 0, so that will cancel. And so if I go ahead and rewrite this, we have 1/2 x sine of 2x, minus negative will cancel, so plus 1/4 cosine of 2x, which is what we have found for the integral of x times cosine 2x dx. So we have the integral of x, which is obviously x squared over 2, minus the integral of x times cosine of 2x, which we have found to be 1/2 x sine of 2x, and then plus 1/4 cosine of 2x. So simplifying everything, we have 1/2 times x squared over 2. I can distribute the negative, so we have minus 1/2 x sine of 2x, and then minus 1/4 cosine of 2x. I can also go ahead and distribute the 1/2. So we have x squared over 4 minus 1/4 x times sine of 2x, and then minus 1/8 times cosine of 2x. And since this is an indefinite integral, I need to add the plus c, and that's the final answer. So now for number 5, we have the integral from 0 to 1 of 1 plus the square root of x to the 8th dx. Now the problem with this one is that there are not really any obvious substitutions you could make. This is probably not a partial fraction decomposition problem, nor is it a trig substitution, nor is it a integration by parts problem. So what you actually have to do here is just use u substitution, but in a different way. So I'm going to go ahead and set u to be equal to that inside function, 1 plus the square root of x. Then I'm not going to derive u, I'm going to go ahead and actually solve for x first. So the square root of x is then going to equal to u minus 1, so then x equals u minus 1 squared. So then now I'm going to solve for dx, or just in other words, just take the derivative of the x equation. So if x equals u minus 1 squared, then dx is going to equal, we're going to use a chain rule, so 2 times u minus 1 to the first, times the derivative of the inside function, but that's just going to be 1. So we just have 2 times u minus 1 du. So plugging everything back into the integral, we have the integral from 0 to 1 of, I replaced 1 plus the square root of x with u, so we have u to the 8th times dx, which is once again equal to 2 times u minus 1 times du. And so to simplify, I'm going to go ahead and distribute the 2 and also distribute the u to the 8th. So we have u to the 8th times 2u minus 2. So then we have 2u to the 9th minus 2u to the 8th. So now when I go ahead and integrate this from 0 to 1 with respect to u, we can just go ahead and use the power rule. So the integral of 2u to the 9th is 2u to the 10th over 10th, or 1/5 u to the 10th. And then we have minus the integral of 2u to the 8th, which is going to be 2 over 9 u to the 9th. So now I can go ahead and substitute back into u, so u equals 1 plus the square root of x. So we have 1/5 times 1 plus the square root of x. If I go ahead and rewrite x, the entire thing to the 10th power, and minus 2 over 9 times u, which is once again is 1 plus the square root of x, this time to the 9th power, and then we can evaluate from the x bounds of 0 to 1. So when I go ahead and plug in 1 for x, we get 1/5 times 1 plus the square root of 1 is 2, so 2 to the 10th, minus 2 over 9 times 1 plus 1, or 1 plus the square root of 1 is going to be 2, so 2 to the 9th. And then minus when I plug in 0 for x, then we'll get 1/5 times 1 plus the square root is 0, it's just going to be 1, and then 1 to the 10th is 1, minus 2 over 9 times 1 plus the square root of 0 is 1, once again 1 to the 9th is still 1. So then we have 2 to the 10th, which is 1024, so we get 1024 over 5, minus 2 to the 9th is 512, 512 times 2 is 1024 as well, over 9, and then minus, we just have 1/5 times 1, which is 1/5, minus 2 over 9. So in order to simplify, I'm just going to go ahead and use a calculator. So when I use my calculator, the final answer I got was exactly, as a fraction, 4097 over 45. That's the final answer.